almost there. 5.5, multiple angle and product to sum formulas. I'm on page 384. You want to follow along. We've got several sections of notable notes. You guys need to have these memorized or written down somewhere, and you need to use them frequently in order to become familiar with them. So what we're going to be doing in 5.5, you're going to study additional categories of trig identities, and those involve the following: sine Ku, cosine Ku. So these are multiple angle formulas. The squares of trig functions right here. The first one being functions of multiple angles, those guys. The third one being functions of half angles. And then the fourth one, products. So we're going to be dealing with all of these. So to get started, you can see we're starting with the double angle formulas, and I'm going to be working example 1, and this is in the book, and then we're going to do problem 11 together. So it says, example 1 says solve. I like solve. That means we have an answer. Solve 2 cosine x plus sine of 2x equals 0. Where does that equal 0? So we're going to rewrite the first part of the equation so that it involves functions of x rather than 2x. So if we look to our note card above, the sine of 2x can be simplified there, and we're going to be using that. So the 2 cosine of x, and instead of sine of 2x, we're going to write in 2 sine x cosine x, and then set that equal to 0. We've replaced the double angle with its equivalent, and now we are going to solve. This is one of the conversations I've had many times in this classroom this year, and I'm looking at two terms. Terms are the parts that are added or subtracted, and what I can see here is a common factor of cosine x, and 2 cosine x for that matter. So we're going to take that part out of each term. What's left in this first term when we divide by it is 1. What's left in the second term when we divide by 2 cosine x is sine x. And now we're back to 5.2 or 5.3, where we were solving these simpler trig functions. So we're going to take each part of that product. 2 cosine x is equal to 0, or 1 plus sine x is equal to 0. Solving the first one, we get cosine x is equal to 0. We know that to be pi halves and 3 pi halves. And on this side, we're going to subtract 1 from both sides. The sine of x is equal to -1, and we know that to be true at 3 pi halves. So the general solution, general meaning all angles, we're going to take pi halves plus 2n pi, because we know that cosine cycles every 2 pi, and x equals 3 pi halves over 2 plus 2n pi. This is the general solution because it involves every single solution. You guys try problem 11 and come back and check. So we're going to start by renaming this double angle, just like in the last one. We know that this can be replaced with 2 sine of x cosine x, and we're going to bring this part down. Sine of x, that's just a regular angle, and this time we can see each term has a factor of just sine x, so we're going to factor that out. The 2 stays this time, so we're going to factor out sine x, and we're left with 2 cosine x minus 1. Again, we're going to take each of those and set them equal to 0. 2 cosine x minus 1 equals 0. So cosine x is going to equal 1/2 over here. Sine x is 0 at, so the sine of x is 0 at 0 and pi. Cosine x is 1/2 at pi over 3, and we're on 5 pi over 3. And we would go ahead and list those in order: 0, pi thirds, pi, and 5 pi over 3. So example 2 gives us the following information. We're supposed to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta, the double angle formulas, and we're given this. Cosine is 5/13, and we're in between 3 pi halves right down here and 2 pi. So we're in the fourth quadrant. That's where we're trying to find our values. We're given this cosine adjacent 5 over hypotenuse 13. We can use Pythagorean theorem and find our sine value, -12. So we now know this, the sine of theta is equal to -12/13, and the tangent of theta is equal to, opposite over adjacent, is equal to -12/5. So we're going to go ahead and use our double angle formulas. All we need right now are those values. So the sine, we'll start with that. The sine of 2 theta is equal to 2 sine theta cosine theta. And we have those values. We're simply going to plug those in. 2 times -12/13 times 5/13. -120 over 169. We're going to do the same thing for the other two. The cosine of 2 theta, that formula is a little different. It is 2 cosine squared theta minus 1. So we're going to take 2. The value for cosine was 5/13. And we're going to square that, and we're going to subtract 1. So 50 over 169, we get a 25 over 169, and we get 50 over 169 minus 1, we get -119 over 169. And finally, the tangent 2 theta. Just an example of how these work. We have 2 tangent theta over 1 minus tangent squared theta. And we're going to plug those values in. -12/5, and on the bottom 1 minus the tangent squared, which is -12/5 squared. That's going to simplify to 120 over 119. Now try number 21 and come back and check your work. So 21 says find the exact values again of sine 2 theta, 2u, cosine 2u, and tangent 2u. We're going to do the same thing exactly, but we're given this restriction on u. We're in the first quadrant from 0 to pi halves, so that allows us to figure out these other trig functions. We get the cosine as 4/5 and the tangent as 3/4. So we're going to go ahead and use the formulas just as we did above, and the sine of 2u, not theta, 2u is 2 sine u cosine u, and the cosine of 2u is going to give, now there's several options for this, cosine squared, that's 2 cosine squared u minus 1. There's cosine squared u minus sine squared u. And there's 1 minus 2 sine squared u. Any one you feel like using. And the tangent has one option, 2 tangent of u all over 1 minus tangent squared. So we're going to plug those values in that we just found and calculate when you get to the bottom of that problem, problem number 11. Nope, 21, excuse me. Number 21, you should be able to come up with this. Sine 2u is 24/25. Cosine 2u is equal to 7/25. And the tangent of 2u is equal to 24/7. So we're just going to walk through example 3 here. We want to write sine 3x, a triple angle, in terms of the sine of x. And that can be written out like this. The sine of 3x is the same thing as the sine of 2x plus x. We're going to use our sum formula at this point, and we have the sine of 2x times the cosine, so this is like u and v that we were doing previously, times the cosine of x plus the cosine of 2x times the sine of x. And we're going to want to simplify that. So now we've got all these double angle formulas. We're going to take this one, sine 2x, this is the same as 2 sine x cosine x. That's this part. And we're going to multiply it by another cosine x. To that we are going to add, we're going to simplify this one first. The cosine of 2x is 1 minus 2 sine squared x. Now we bring this guy down, times the sine of x. We're going to simplify the first part. We get 2 sine x cosine squared x. To that we are going to add, we're going to add the second part, which has been distributed. So when I distribute that sine x, I get sine x times the 1 minus 2 sine x squared times sine x would give us sine cubed x. Simplifying that, I see now 3 terms. We want everything in terms of sine. So we're going to take this and rename it as 1 minus sine squared x. And we have 2 sine x out in front of that. To that we're going to add what we already had, sine x minus 2 sine cubed x. We're going to go ahead and distribute the first part here to both parts. We have 2 sine x times 1 minus 2 sine x times sine x squared, which gives us 2 sine cubed x, plus the remaining part that we haven't worked much with, but I think we're going to get to that here in a minute. And from that we can see 2 sine x plus sine x, that gives us 3 sine x, and we get negative 2 minus 2 more, we get minus 4 sine cubed x. Remember, like terms are those terms that have the variable, same variable, to the exact same power. Go ahead and try number 27, and you're going to come back to part 2 on the recordings to check your solution.